All right? Okay. It says microphone is off. I don't know. Okay. All right, it's recording. All right. So last time, I think we kind of did a little bit more on point location. I pretty much finished that up. And we covered the problem of detecting intersections between line segments. And we saw a way to go take that algorithm and then turn it into a point location problem through persistent data structures. So today, we're going to talk about kind of the last thing that's sort of related to all of these point location or polygon processing algorithms, which is polygon triangulation. So polygon triangulation is sort of what its name sounds like. It's the problem of given a polygon, or more generally a planar map, and then decomposing it into a set of triangles. So we're going to take some polygon as input, chop it up into little triangles, and then store all of them, right? And so things that you would want to use this for is if you're going to, like, say, take a planar map as input, you could use triangulation theoretically to chop it into triangles, feed that into the Dobkin-Kirkpatrick algorithm, and then do point location on the planar map. But in practice, the reason that you usually care about polygon triangulation is for computer graphics. So typically, if you have some path, like say like an SVG file or some other type of data set like a map, and you want to render it, then the fastest way to render it on a modern computer is to chop it into little triangles and then feed it into WebGL or whatever. And then it's going to rasterize each of those triangles like ridiculously fast in hardware. So we usually care a lot about triangulations and getting them right because we care about drawing things and looking at things at the end of the day. So a few quick words here, right? And this is all going to be kind of review here. If we have a simple polygon, right, and if you remember that's a polygon where it doesn't have any self-crossings or holes, then we could pretty easily compute the number of triangles in there, right? We can do it exactly. So assuming that such a triangulation exists. So we'll say, OK, given a polygon P with n vertices, then we know two facts immediately, just because it's a polygon, right, sitting in the plane. So if we triangulate it, the Euler characteristic tells us that v minus e plus f is going to be equal to 1, right? So that's a fact from topology, right? And we also know, if we triangulate it, that 2e minus v is equal to 3f. All right, so this is the Euler equation. And this is the Den-Somerville equation. But we have this extra term here, which I'll underline. And this is basically counting the number of edges twice, only on the interior. For the edges on the boundary, of which there are v, we're only going to count them once. So to illustrate how that looks, imagine I have some polygon triangulation like this. Right. So the total Euler characteristic of this thing is 1. And so I have v vertices out here. And I have additionally v edges on there. So if I do 2 times the number of edges, but then to count all the faces and then subtract off all the ones on the boundary, that's 3 times the number of faces, right? Because each face gives you 3 edges. All right? So from this, we can conclude a couple of things. First is if we take this equation here at the top, multiply everything through by 2, then this thing here will just be 2v minus 2e plus 2f equals 2. All right, so we have 2e minus 2v plus 2f equals 2. And so if we solve for e, right, for or 2v, not 2e, right? So if I solve for 2e on this side, then I get 2e is equal to 3f minus v. Then, or no, 3f plus v. All right, then I take this, plug it into here. So that gives me 2v minus 3f minus v plus 2f equals 2. And And then I rearrange all of the terms, right? So I end up with v minus f equals 2, or in other words, v equals f, or f equals v minus 2, right? So what do we conclude from all of this? At the end of the day, right, any triangulation, so from this whole derivation there, any polygon P with n vertices has a triangulation, or given a polygon P with n vertices, any triangulation of P has exactly n minus 2 triangles. Right. Now, this doesn't say that such a triangulation necessarily exists, but it just says that if we ever did construct one, it's always going to have the same number of triangles. You can't change that, right? Okay. So how do we go about building such a triangulation, right? Well, actually no, first how do we prove that such a triangulation exists, right? That's the next step. So, okay. So we want to try to show that such a triangulation of P could exist in some sense, right? So the way that we're going to do this is we're going to first introduce a concept here. So if you remember in sort of these pictures, right, or a picture like this that I drew. So imagine I have some polygon, I cut it into triangles, right? We have these edges on the outside, right? These are just going to be the normal edges of the polygon. And we have these edges which are on the inside, right? So we're going to call these edges on the inside, like these things here, diagonals, all right? So we'll define the following concept. A diagonal of P is a line segment contained in P, not crossing any edge, and having two non-adjacent vertices of P as endpoints. All right? So hopefully that's clear, right? So basically, we're just going to think of these diagonals as like lines that we could draw through the polygon that don't cross. So, so this line segment here, that's a diagonal. But if we took this line segment here, that's not a diagonal, so it's no good, because it crosses one of the boundary edges of the polygon. And so if we also took like an edge out here, because it's outside the polygon, again, not a diagonal, and we can't connect to adjacent vertices. So we're going to rule out the edges of the polygon. All right, so you can basically think of this as like measuring. All right, so here's sort of the idea, right? So how we would construct a triangulation is that we could basically first locate some diagonal, cut the polygon by that diagonal into two separate pieces, and then repeat until eventually all that we're left with are triangles. So the general idea, right, is that if we can at least find one diagonal, we can always split the polygon, right? And then we can just proceed with this splitting until eventually we're done. So what we need to show next is that any simple polygon, which is not a triangle, has a diagonal, right? So that's our first lemma, right? Any simple polygon has at least one diagonal. All right, so why is this true? Well, we can basically prove this by a case analysis, right? So just pick any vertex in the triangle, all right? So the first concept is we pick any vertex V. There are two cases. the first case, right, is that V can see a diagonal. So if we have some vertex here, whatever, call this V, and somewhere out here, there's another vertex. So the first case is V has a diagonal, which is easy, right? So we're done. The second case is that there is no diagonal visible from V, right? So this means that V has to be, first of all, a convex vertex, right? Because if it was concave and it's on the interior, right, then there's still going to be like some outward visible chunk of the triangle. So this would be, or some outward visible part of the polygon. So if we have a case like this, right, where V can't see a diagonal, there is no vertex that's visible from this point V, then the two neighbors of V have a diagonal, right? In which case we say that V is an ear, right? So the other case is that the neighbors of V have a diagonal. Another way to say this is that V is an ear.
Just curious, what about polygon with only 3 vertices?
Any simple polygon with more than 3 vertices. That's I actually wrote that in my notes, but I forgot to write it up here. Yeah. Right, so these are basically, if we have a triangle, this is kind of vacuous, right? So we basically don't have to worry about that case. In fact, that's where we want to ultimately get to. So, okay. With this, we've pretty much established what we wanted to prove, right? Because what we can do is we can just apply this lemma recursively and show that any polygon can, just continually be split by cutting it along diagonals into tinier polygons until eventually all we're left with are triangles, right? So we have first theorem for today here. Any polygon has a triangulation. So, okay, no big deal, right? So a couple of interesting things to note about triangulations, right? So we've already seen triangulations in the concept of Delaunay triangulations of point sets, but there's a few interesting things that we can say about triangulations for polygons. One is, first of all, that these triangulations are not unique, and there could potentially be a lot of them. So what we would like to do is have some way to count these triangulations, maybe, so that we could perhaps put an upper bound on the total number of triangulations that could exist. As maybe like an academic type exercise. So counting them at first seems like it might be a little bit difficult, but there's an interesting alternative way to look at a triangulation of a simple polygon that makes it much more clear how many possible triangulations there can exist. And so here's the way we look at this, right? So we can form the dual of a triangulation, right? So we'll start with some, weird polygon like this. Whatever. All right? And then we'll draw our diagonals here, cut it into triangles. Just connect them any which way. Right? So the dual of these is going to be a graph where each vertex is one face of this triangulation. And each edge here is just a flipped edge in the original triangulation. So a couple of things to note about this dual graph. Right? So the first of all is that if I cut any vertex out of this graph, right, the entire graph is going to be disconnected. Why is that true? Well, if I take any triangle and I cut it from the original polygon, then I've disconnected the original polygon, right? So this graph is one connected. So I guess the 0th point is that it's a graph, right? Not an actual cell complex. So not even like a cell complex here. The second, it is one connected, which we can check directly over there. And then the final point is that every node has at most degree 3, right? Because they're all triangles. Has degree less than or equal to 3. So what does this mean, right? Well, there's another word for such a graph. Does anyone know what it is? A binary tree, actually, but very close. It's a binary tree. So this is a binary tree. So if we take the dual, right, of one of these graphs, right, or the dual of one of these triangulations, we end up with a binary tree. And so if we want to count the number of binary trees, this is a pretty well understood problem in combinatorics. You see it in a bunch of different places. And so what we can conclude, right, I'm going to erase some stuff here. Probably all the way up. So the conclusion of this is that there are as many, this is a kind of theorem, are, actually I should say at most, Cn minus 2 triangulations of a polygon. Right, where Cn minus 2 is the nth Catalan number, right? So we'll say where Cn is the nth Catalan number. And the Catalan numbers just count the number of binary trees on n nodes. So this, you can look up the definition for them. You know, it's, you can also calculate it through like dynamic programming. So the number of these things is, I guess it's 2n factorial over n plus 1 factorial n factorial. Right? Or you can write it, you know, as like 2n choose n or something like that, or 2n choose n plus 1. Then divide by n, something like that. Yeah. And so this is actually a tight bound. And the way you can reach this is for convex polygons. So if I take some convex polygon, the number of different ways I can chop this up, right, will create, you know, trees that'll look like each of these things, right? So if I just take a convex polygon with n plus 2 vertices, then all of the different triangulations of that will yield all of the different binary trees. So you can map, you know, in a one-to-one relation, you know, any binary tree that you pick, and then any triangulation of a convex polygon. For simple polygons, you're generally more constrained, and then the exact details of how many possible triangulations could exist depend on the particular polygon that you would pick. So I should say convex polygons. So, okay, that's kind of interesting, right? Another interpretation of the Catalan numbers is that they also count the number of different ways that you can have n evenly matched parentheses. So if you think of like parsing out, you know, a set of parentheses, right, then the resulting parse tree is just some binary tree. Or another way that you could think of that is that if you do an in-order traversal of a binary tree, you get a set of parentheses, right? So they're just two different ways of looking at the same kind of thing. All right, well, that's kind of fun, but all right, not the most important thing in the world. So, okay, so we've also so far been talking about mostly simple polygons, but it turns out that this is actually sufficient for any polygon. So we can actually take any complex polygon and then turn it into a simple polygon with two easy steps, right? So we'll say, what about complex polygons? Not much harder to triangulate. The first thing that we do is we have to resolve self-intersections, right? And we can just use the sweep line technique that we did before. right? And then the second thing is we have to cut each of the loops, right? What do I mean by that? Well, let me draw a picture here. So suppose we have some crazy complex polygon like this. Right, and maybe we have like a loop on the inside going around like that. All right, so we have this weird mess of a polygon. I claim that we can turn this into a simple polygon in these two steps. So the first thing is we get a loop. We have some self-crossing like that, right? Well, we use the sweep line method that we talked about last time. We detect these vertices, then we just have to cut it, right? So we basically cut out these two edges. And then we're basically going to make two loops like this, right? So one that goes in, one that goes out like that, another one that goes there like that. So that's pretty easy, right? Just kind of detect all of these crossings, chop them out. Now that's simple, right? Now we got this loop, right? So all we have to do with each of our loops is we just find any vertex here. You can just do an order n scan of the whole polygon until you find some edge, right? And then what we do is we walk out from this vertex here, right? And then when we're walking, actually I should change the order here. So when we get here, we'll just walk out to this point. Then when we're all done, we walk back there. So we're just sticking an edge in the loop, right? So you can imagine that what's happening is you walk along here, we walk in, then we walk down around the polygon, when we come back, we walk back out. All right. So in doing so, what we've done is we've taken some horrible mess of a complex polygon with like weird loops and holes and self-crossings. Then we just have to cut up its topology and glue in these extra edges here, and then the resulting polygon that we get is a simple polygon. So this step you can do in linear time by just scanning over. You just pick one vertex on the loop, then you scan over all of the extra points, and then you basically keep track of this edge between them. And anytime you see a crossing with some other vertex inside one of the polygons, then you just update this edge so that it moves to like a different vertex of all of these other polygons. So that's not so bad. And so this you can do in order n, and then this one takes order n log n, right? So if you only have loops and you don't have to worry about the other stuff, you can just do this conversion in like linear time. So it's really cheap. So OK. So convex polygons, no big deal, right? OK. So all right, the problem that we have now is that we want to triangulate a simple polygon. So I'm going to erase this stuff. Right. Right. So I will keep this here. And the reason I want to keep this here is because it's going to be the basis for the first algorithm. So one interesting thing about this dual graph and those vertex types that we talked about earlier is if we look at these terminal nodes, or the leaves of the tree, right? Each of these leaves of the tree happens to be a convex vertex with a diagonal that crosses it directly, right? So in the case of this dual graph version here, each of these terminal vertices is an ear, right? So we have the following observation. So we'll say in dual graph, each terminal vertex is an ear, right? So does everyone follow this, right? So remember, ear is like one of these things where you can just take the two neighbor vertices, connect them, and then that's a diagonal of the polygon. The conclusion of this is a result that has a funny name and is somewhat famous. It's sort of obvious, though. It's the Two Ear Theorem, right? This is the Two Ear Theorem. And it just says that every simple polygon has two ears. Has two ears. So here is the first trivial algorithm that we have for triangulating a polygon, which is you just walk over all of the vertices until you find an ear. You cut that ear out of the polygon, and then you repeat until you eventually removed all of the ears from the polygon, and then you're just left with a triangle, right? This is the ear clipping algorithm. So sounds pretty easy. It's actually pretty spectacularly inefficient, right? So we basically just say, while P is not a triangle, find and cut an ear. All right. So anyone want to take a guess on how long this takes? All right? Or any ideas? Well, I mean, the first step is how many iterations are we going to have to run this loop here, right? So there's going to be n minus 2 triangles, so this only runs n minus 2 times. So the question is just how long does this inner part take, right? Ideas? I've not been very specific, right? So, but let's suppose that we find an ear by just scanning over all vertices, right? Then once we find a vertex, we look at the two neighbors and then just check if that's a diagonal. So we just loop over all vertices until we find a convex vertex and then test the diagonal. So to test if that is a diagonal, we have to loop over all of the remaining edges in the polygon and then check whether each of those, remaining edges happens to be a diagonal, right? So we have to check that edge if it intersects any other edges. We can just do that by brute force. Is everyone kind of getting the idea here? So guess on how long this would take, right? So we have to first find the ear, right? The first ear. That could take order n time, right? Then we have to check that it's a valid ear. That's another order n operation. And if it's not a valid ear, then we have to go to the next one. So we have to keep running that loop. So this is basically a quadratic time algorithm to find one ear, right? And then once we found that, we have to run it n times. So the total cost of doing this would be order n cubed, right? So this is kind of a dumb algorithm to do polygon triangulations. You probably wouldn't want to implement this unless you know your polygons are going to be very tiny and you really just don't care, right? So for sufficiently small things, all right, whatever, you can just do ear clipping. It's not going to make any difference. But we would obviously like to have something that runs a little bit better than that. And it's not a big deal to actually modify ear clipping and get it down to quadratic time, right? So here's all we do, right? So here's the sort of modified ear clipping. I mean, the real problem here, right, is that every time we get to one of these, vertices, if it's an ear, right, then we can do something with it and we cut it off, right? But if it's not an ear, then we have to just skip it and keep going. But if you remember, right, when we were talking about diagonals, there's sort of two cases for each vertex. We have the ear case, which is the easy case, and then we have the not an ear case. And so the question is, can we do something with the not an ear case, right? Well, in the not an ear case, there may not be an ear connecting that vertex, but it's at least going to have a diagonal going somewhere. So all that we have to do is we just say, OK, we'll say while P is not a triangle, we'll just say V is just any vertex. So we'll just say any vertex in P. In P. Then here's what we'll do, right? We'll just say for each edge, or for each edge V in P. All right, so what we're going to do is we're going to basically, or for each vertex U in P, we'll say either U crosses, how do I want to do this, right? Yeah. Here's what you do, right? I think I wrote this a little bit wrong, right? So here's basically the idea, though. I haven't actually implemented this algorithm, right? Because we'll see a better algorithm in a moment. But OK, what you do is you start out testing for an ear, right? Then you search through every edge. If an edge violates that ear, then you take the vertex of that edge, which is closest, and you move that to be the visible vertex from the vertex V, right? And you continue searching until you find something which violates that vertex. So when you're all done, right, in this sort of hand-wavy way, we'll basically end up with one of two cases. We'll say if V is an ear, cut it. Otherwise, split P along diagonal, recursively triangulate pieces. The trick here is basically how you find this splitting diagonal as you're doing this search, right? The details are kind of messy, and I don't really want to go into it today. But suffice to say that this can be done at the same time as when you're checking whether or not it's an ear, right? And as a result, because we didn't have to do this initial search to find some ear to get started with, we could just pick any vertex. This total algorithm, the total time of running each of these intersteps here is going to be order n. And even though we have this recursive phase where we split them apart, every time we run one iteration of this body of the function, we're going to at least kill one edge, right, or one diagonal. And so the total number of iterations will be order n, and each iteration requires order n time. So the cost of doing this modified ear clipping is order n squared, which is still quite terrible, actually. We can do far better, right? So you can do this naive ear clipping, and if you actually search online for polygon triangulation, most codes that you'll find will do this, right? Which is because most people, I think, just aren't aware of the fact that there are far better answers to this problem. You can find maybe one or two things that do this method, but it's just too complicated and not really worth worrying about. And so that's the easy kind of answer to this polygon clipping problem, right? So you can do something like this. But we would like to do better than order n squared. So the obvious lower bound is order n, right? I mean, we have to process at least every vertex once. But even if we could get within the ballpark of, say, order n log n, that would still be like pretty good, way better than order n squared. So the next algorithm that we're going to see, right, will reach this order n squared. But before doing that, I want to look at a few special cases first, right? So for a general simple polygon, maybe order n squared is as good as you could do, or maybe not. I don't know. We'll see. But there are certain specific simple polygons where you can do much better and where it's very easy to triangulate them. So the first case is convex polygons. So I'll just erase all this stuff. I don't think I even need it here. All right. First special case, convex polygons. There's a trivial one. Convex polygons. So here's how you triangulate a convex polygon. Just say pick any vertex. Triangulate by ear clipping in, say, counterclockwise order, right? So you basically use the same ear clipping technique that we talked about, but because it's a convex polygon, we can clip them in a nice order, right? So here's the neat thing. So if I basically start from the vertex immediately adjacent to any vertex here, then I can just clip this ear, right? Then similarly, I am left with now this triangle, so I can just clip that ear. And when I'm all done, I've triangulated the entire polygon. So it's just a scan along each of the edges, right? Another way to say this is that in a convex polygon, every vertex is an ear, right? Why is every vertex an ear? Because I can say, first of all, they're all convex, right? And by the definition of convexity, I can just draw a diagonal between them, and it's going to be completely contained in the convex polygon. So another way to think about this is that in convex polygons, every vertex is an ear. So ear clipping runs in linear time, right? So it's really, really fast for convex polygons. Now, there's another very important class of polygons, which is a little bit larger than convex, and which can also run this ear clipping algorithm in substantially faster than quadratic time. And these are called monotone polygons. So we've already seen this concept of monotonicity in the case of 2D convex hulls, when we learned about the fast algorithm for computing a 2D convex hull using monotone chains. All right, so remember, a monotone chain is just it's like a sequence of points, right? Where if we construct like a polygonal line, right, or a polyline through each of those vertices, right, then if you take any line and you intersect it with that polygon or with that chain, you're going to find that it will intersect at exactly one point. For polygons, this is basically the same definition. So we have to first pick some axis, right? So I'm just going to do it for the x-axis for now. So we'll say x monotone. So we'll say a polygon P is x monotone if and only if any vertical line intersects P at most twice. Here's kind of a picture, so if I imagine I draw some weird thing like that. Right? Then if I take any line that I like, there are exactly 2 points where the line crosses the polygon. All right? So here's an interesting fact about monotone polygons. Every monotone polygon is the union of two monotone chains. So we're going to have an upper chain and a lower chain. So here is the concept. We'll say a monotone chain, or we'll say an x monotone chain, is a polyline which has at most one crossing. And we'll say any x monotone polygon is the union of two x monotone chains. How do you check that? Well, what you can do is basically take any line, right, intersect it with the polygon. It's going to intersect it in two places, right? You just take the upper intersection, that becomes the point on the top chain, and then the lower intersection becomes the point on the bottom chain. So in this way, you can basically split this polygon here into two chains, like that, then another chain here, like that. All right, this is kind of where that monotone chain polygon our convex hull algorithm gets its name, right? So we remember how that works, where we're just maintaining these two different chains for the polygon, and then we're going to basically be inserting the vertices into each of them independently. I mean, it's also obvious here that every convex polygon is an x monotone polygon, right? Or it's monotone in any axis, right? So that's actually another way that you could even think about defining a convex polygon, which is that convex polygons are monotone for whichever direction you pick, right? So, okay. So far, so good. And so monotone polygons are nice. And it turns out they're pretty easy to triangulate. We're not going to even have to, though, triangulate a general monotone polygon. The way we're going to do things is we're actually going to focus on an even simpler kind of polygon, which is a unimonotone polygon, right? So a unimonotone polygon, a polygon is x unimonotone if one of its chains is a single edge, right? So the idea here is that one of these chains will just be like boringly trivial, right? So we'll have one chain which could be like some crazy mountain range going along the x-axis, and the other one is just going to be a line, right? That's it. So let me draw a picture of this. I'm going to erase these definitions here to make some more space. And we will see how it is really, really, really easy to triangulate a unimonotone polygon by ear clipping, right? We're just going to basically combine this convex ear clipping thing with a kind of smart order for trimming off the vertices. So get space back here. So we're going to say triangulating unimonotone polygons. All right. So here, let me draw a picture of a unimonotone polygon. Let me kind of I mean, you can kind of draw your own, follow along with this idea. So here's a unimonotone polygon. So we have this chain here, which we're going to call, let's call this C, and then we have some edge here. We'll call this vertex V0 and V1, right? So what we want to do is triangulate this thing, right? And the way we're going to do it is we're going to basically scan along this upper chain, right? And we're going to maintain two stacks, right? The first is that we're going to have a convex polygon, which will be something that we can triangulate easily, right? And then we're going to have these extra ears that we're going to just trim off, right? So the idea is that we're going to basically run ear clipping on this upper monotone chain until all that's left is some convex polygon. And then we can take that convex polygon and then just crunch through it really quick. All right, so here's the high-level idea. Scan through C, trim ears, take resulting convex chunk, and triangulate. So the idea is that we're going to have a stack of vertices that we've seen so far as we scan through C. And then every time we get to a new vertex, we're going to insert it into this stack. And then we're going to recursively walk back along this stack, or we'll just scan along it, popping off vertices until we've basically trimmed off all of the ears. So let's go through this right now. So we'll start from this vertex V0. We hit this first point here, right? We'll call this one here P0. And we get to P0, and so we just push it onto the stack, right? Next we get to P1. And here at P1, we see that this chain here going from V0, P0, P1 was an ear. So we pop P0 off the stack, add in this diagonal, and then push P1, right? So I'm going to call this the stack here. So we're going to kind of simulate the execution. Next, I get to P2. And so here, P2 and P1 and P0 is not a monotone chain, so I'm going to just leave it here, push it back on. All right? Then I get down to P3. All right? So I see now that P3, P2, P1 was an ear, so I'm going to pop those off the stack, push P1 on it, and then trim this ear off. Next, I get to P4. I see that P4, P1, P, like these were here an ear, right? No, right. I popped off too much. I shouldn't have popped off P1 when I did the P3 vertex, right? So I have P1, P3. I get to P4. P4, P3, P1 is an ear. Trim that. So that's all good. Now I'm basically back to P1, P4. Now I get to this vertex here, P5. So at P5, I look back, I got another ear here, clip that. All right, and then I got another ear all the way back here, so I'll go clip this. And I'm back to just a stack with P5 on it. I get to this vertex, P6. It's not an ear, so I'll just leave it. Or actually, I guess that would be an ear. Yeah, I guess this is an ear. Maybe I drew it a little bit funny. So now I'm at P6. Get to this point here, which is P7. All right, not an ear, so push it on. Oh, yeah. All right, let's make this more interesting here. All right. Here we go. P7, and then finally I get to P8. Again, not an ear. And so the idea is that every time I do this, right, the resulting thing that I'm left with here is basically a convex hull, right? Or you can think of it as the complement of a convex hull. And so when I get to V1 here, these are just going to be a set of vertices along some fan extending out from V1. And so at the end of it, I just connect these diagonals here, and then I've triangulated this monotone polygon, or the unitone monotone polygon completely. All right, so that's how you triangulate a unimonotone polygon in linear time. All right, so the cost of this is order n. And space All right, so this is really, really quick if you actually implement this, right? Because it's just like checking if one of these vertices is an ear is just a matter of checking the concavity of each edge, right? So if I want to check if this, was an ear here, all I have to do is just do a left-right test, right? So it's just, orientation test for each vertex that I push onto the stack. And then when I'm all done, basically add these fans over here, for the last vertex on the chain, and the polygon is triangulated. Ta-da! All right, so that's really great. So the question then is, how do we start from some simple polygon and then turn it into unimonotone pieces efficiently? All right, so that's the next question that we have, right? So if we can do that relatively fast and say like polylog time, then we can triangulate our polygon pretty fast, right? So the way we're going to do this is not the same way that DeBerg does it, because DeBerg's algorithm is a little more complicated. Instead, we're going to do a simpler thing using trapezoids again, right? So we're going to construct a trapezoid decomposition. Then from this trapezoid decomposition, we're going to turn our polygon into unimonotone chunks, right? And then we're going to just run this unimonotone triangulation algorithm on each of those unimonotone chunks. And this whole thing will basically go in order n log n. So this is the idea, right? So we've already seen this thing. I'm going to erase this. Hopefully this is clear, right? The unimonotone triangulation stuff, right? DeBerg's algorithm is way more complicated. They have like this crazy notation for, like split and merge vertices and a bunch of weird cases, and we're not going to do it. So it's like this is the simpler way, right? So the trapezoid method. Okay, so step 1, split polygon into trapezoids. We've already seen kind of how to do this before, right? We know that we can do this in n log n time. We'll see a different algorithm today, right? But it's the same basic idea. 2, we're going to basically cut some of the trapezoids along diagonals. It turns out when we're all done with that, right, doing this very simple like diagonal cutting, right, the resulting chunks that are going to be left of our polygon will all be unimonotone pieces. And from those unimonotone pieces, we'll just run the previous triangulation algorithm. So we're going to triangulate unimonotone pieces. And in practice, if you want to do this really fast, then you have to actually do each of these 3 steps in parallel, right? So you have to basically say that, like, as I generate a trapezoid, I will basically check for a diagonal, and then once I make a cut, then I'm going to run the triangulation on it. So if you're running like a really industrial scale Polygon triangulation algorithm, it's really just a matter of like concatenating all of these 3 things together. So you can think of these as like streams in a way, right? So this algorithm is going to be streamingly like spitting out trapezoids in some order. And this algorithm is going to be taking these trapezoids and cutting them. And then as it's cutting them, it's going to be spitting out monotone pieces. And then the triangulation algorithm is going to consume those and then spit that out. And if you concatenate them in that way, you can do it with much less intermediate space and without building copies. But it becomes a lot more complicated, right? So we're going to think of this, not as being like a glued together thing, but we'll just view them as 3 discrete steps, even though in practice, if you wanted to do this like really, really fast, you have to glue them all together, right, in some kind of messy way. Right. So trapezoid things, we'll come to this in a moment, but we already know kind of how to do that, right? We have at least a algorithm for cutting things into trapezoids. We'll see another way to do it. But this is a little bit tricky, right? So we already know how to do this, right? We know how to do this, kind of. We're going to focus on this one, right? So how or when do we make a cut in one of these trapezoids, right? So here's, let me draw a good picture here. Right. I mean, it almost doesn't really matter, I guess. Is there something to this? No. Whatever. I'm just going to adapt this picture. All right. So here's the idea. So we'll start with some polygon. Looks like this. I don't know. Right. Okay. So hopefully y'all kind of remember how to do the canonical, or at least what these trapezoids look like, right? So the way you form a trapezoid decomposition is you just go through, for every vertex in your set of line segments or in your polygon, you drop 2 lines, right? You have one that goes below it and then one that shoots up. And then you just intersect those lines with whatever segments happen to be directly above or below that vertex, and then you cut a trapezoid out. Or in some of the extreme cases, like on the corners, you get a triangle. So let's do this here. So we start out here, drop that, we end up with one trapezoid there. There, another trapezoid there, trapezoid there. Another trapezoid here, here. All right, we're just cutting it into these like little sort of like chunks or slabs or trapezoidal bits, right? Okay, so where do we put in diagonals? Well, there's really only one place that does kind of make sense to put them here, is that we can just look at each trapezoid independently, and then if a trapezoid happens to have 2 common vertices, right, that intersect on either the left or the right slab, then we just cut that, right? It's really easy. So we'll basically just say, okay, well, we have these 2 vertices here, which have a common point, so we'll put that diagonal in here. Similarly, in this trapezoid, these 2 vertices are touching, so we'll cut there, cut there. I think we have to cut here, and I guess we have to cut there. Those are the only places the trapezoids would really like give us any help in it, right? So there's like the obvious place to put these diagonals, and they're called the obvious diagonals for a reason, right? Because that's the only ones you can cut. So you just cut them wherever there's 2 vertices that touch in a trapezoid. And it's going to be a diagonal because they're both in the same trapezoid, right? And so within the trapezoid, there's only these diagonals to cut, right? So we basically...
I think I see another one we can cut.
Is there one I missed? Well, they're called obvious, but maybe I'm blind. Is there one I missed here?
4 trapezoid in from the left, the red.
Ah, you're right. I missed an obvious one. Okay. So they're called the obvious trapezoids, but they're probably only obvious to a computer. I don't know. Whatever. So we basically cut out the obvious trapezoids. I'm going to put that in scare quotes. Specifically, these are diagonals that are basically contained in trapezoids. So basically, these have to be the diagonals of the polygon that are completely contained in one of the trapezoids. Now, here's the cool thing. So if we do this, right, the resulting bits that we're going to be left with are all unimonotone, right? I mean, it certainly looks like it here, right? So if we take this trapezoid along this edge here, then this is a unimonotone chunk there. Similarly, we have a unimonotone chunk right here. We have a unimonotone chunk there, unimonotone, 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 right? So if you just do this cutting, the resulting bits that you're going to be left with are all unimonotone, right? Well, why unimonotone, right? Well, the first thing is that it's pretty obvious that they're going to be monotone, okay? Because if you just glue together trapezoids, right, left to right, then the resulting polygon is always going to be monotone, right? So monotone is easy. Why is it unimonotone, though? Well, if there was more than one vertex along either edge, right? So suppose that there was like, multiple vertices here and multiple vertices there, then there's going to be a common trapezoid between those two vertices. Then we can just split that, right? So not only are these all monotone chunks, they're all unimonotone chunks, right? And then you just take each of these unimonotone chunks that you've now cut it apart into, and you run that previous triangulation algorithm on it, and you're done. Life is easy, right? So is that clear to everyone? Make sense? All right. So finding these diagonals is basically like order n on the number of trapezoids, and we know the number of trapezoids is basically order n. So this part is order n. Similarly, triangulating the unimonotone pieces, also order n. So the question is, how do we do this fast, right? How do we split this thing into trapezoids? Any ideas on how we'll do the trapezoid decomposition? Concept. So remember, they're kind of related to like slabs, right? Sort of like slabs, but they're a little bit simpler than slabs, right? Looking for 2 words, or maybe 1 word if you hyphenate them. Like an algorithm technique, right? We've already used it like in the past 2 lectures, like twice, right? Come on, guys. What do we call it when you walk along one of the axes? Yes, we're going to use a sweep line method. All right, so we saw how to do the trapezoids by a randomized incremental construction, but today we're going to do it using sweep line. Trapezoid. All right. This is pretty much exactly the same thing that we did for line segment intersection detection, right? All that we have to do is, as we're scanning left to right, we maintain a list of line segments, right? And then when we insert a vertex, instead of like checking for an intersection or whatever, we just emit a trapezoid, right? So here, you can kind of go through the different cases. So let me draw a picture. Right. So this is kind of the idea. Is that, okay, we get to a vertex here. So there's sort of 3 different cases that we can run into. One is that we have like a triangle here, or one is we have a corner. So the corner basically becomes a start new trapezoid. So basically say scan. Let me just go put the high-level idea here. Scan left to right. All trapezoids left of line are processed. All right. So if we get to a corner here, we start a new trapezoid. If we hit some edge like this here, we have to basically like delete edges, right? And generate trapezoid above and below. Right? So we basically say start new trapezoid, insert edges, emit trapezoid, delete edges. And then finally, we have like this scenario here, where a vertex is somewhere in the middle. And this can basically be emit. This is two trapezoids. We emit one trapezoid. And then delete, or no, replace an edge. All right, so those are kind of the cases that we have to worry about. So as we sort of scan through this here, we come to this point. We emit a trapezoid here, a trapezoid there. We get to this sweep line. Get to this point, emit this trapezoid. Here we get here, we emit this trapezoid. We get to, let's not worry about the degeneracies right now. All right, so we get to this trapezoid, and then process that. Here we split this one. Then we get to this point, emit that, and there, then we're done, right? So maybe this makes sense, right? So I'll just number them in the order in which they would be emitted here. Say this is 1, 2, 3, 4, 5, 6, 7, and 8. All right, so I don't know. Maybe that's clear. Hopefully this makes some sense, right? I mean, we're basically doing exactly the same thing we did last time for sweep line, right? We just have this ordered list of segments, right? And then every time we get to a new vertex, we have to basically update that list of segments. And then just as we're doing that updating, we're also emitting trapezoids, right? So it's exactly the same technique that we used for doing, the same sweep line thing. So given this, right, we can do this simple diagonal trick here, right? And then triangulate all the unimonotone bits, and we're done, right? So this gives us the time complexity of doing this is, well, we start with some initial polygon, and we have to sort the vertices in some order. And after we've done that sorting, which is basically an order n log n operation, processing these events requires us to update this tree over here. But doing that updating is like an order log n operation per insert, delete, or tree access. And we have to do order n of those. So the total cost is order n log n plus n times log n. So order n log n, right? So the total cost of doing this, well, we have order n here, order n log n, n, so order n log n. All right, so that's how you can do polygon triangulation in order n log n time. It's not too bad. You just have to do this step, which is a little bit tricky, right? But it's not even pretty horrible, because assuming your polygon is simple, then you don't have to worry about all like the sort of weird cases where you have multiple nodes crossing in this tree, right? So it's pretty straightforward. You can generalize this too to work on general planar subdivisions, right? So it's not just for simple polygons. It really works for pretty much anything. So for planar subdivisions, so you can basically run this thing through and then process it with the Dobkin-Kirkpatrick method and then use that for point location, although you're probably better off using persistence or some other technique, right? But you could use it to triangulate some general map all in one shot. Now there's a trick, right? It's very complicated, and we're not going to go into it. But it turns out that you can actually speed up this step a lot, right? So you can change this from running in order n log n to order n log star n using a very sophisticated randomized algorithm invented by Seidel. And so you can construct those trapezoids in order n log star n. Trapezoids in order n log star n. So if you know log star is a very, very slowly growing function. So that's like the inverse Ackermann function complexity here. So this is like really crazy, crazy slow. So you can do it like that.
Same as the inverse Ackermann?
Yeah. Right, so this is very fast. You can do it like crazy fast. But it turns out that there's actually an even faster algorithm, right? You can actually do it in order n time. I don't understand this algorithm, though. So I won't even bother to present it. In fact, I don't think anyone understands this algorithm except for maybe a small handful of people. Order n is possible. As far as I know, no one has ever implemented this method, right? There is sort of there's Bernard Chazelle's galactic polygon triangulation algorithm, right? It's like this algorithm is insane, right? It's like the paper is like 20 pages of dense mathematics, and apparently it works. I mean, many people have checked this, I guess, right? But I cannot claim fully to understand how that algorithm works. And as far as I know, no one has ever actually implemented it. But there is an algorithm that reaches order n. It's an open question whether or not there is a simple algorithm that reaches order n. But it is possible to triangulate a polygon in order n time, right? The details of it, though, are insane, right? Like completely insane. You will probably never be able to like understand this algorithm. It's maybe not worth trying, right? Yeah, but suffice to say, it uses like this huge collection of like crazy ideas, right? It's like very, very complicated, right? But it's order n, so perhaps for sufficiently large polygons, there's a point where it becomes profitable. Right. So how am I doing for time right now? I didn't bring my phone with me today.
To have n better than n log star n, like.
Yeah. Well, so yeah, so that.
Really very practical.
Yeah, and actually, like even though it's like a log star, there's a lot more pointer arithmetic. In practice, this is really like the one you want to go with, right? This is the default Polygon triangulation algorithm. Now, I didn't bring my phone. Can you tell me what time it says up there?
210.
2:10. Okay, that's not a lot of time, but that's fine. There's not much to say here. So, right, there's one other thing I wanted to talk about. Right, so art gallery problem. So this is kind of a problem that's more famous for having a cute name than for having like any real application. So I'm not going to spend too much time on it. But it's a neat thing that you can do with triangulations besides drawing stuff or point location. So it's probably worth saying a little bit about it right now, since I don't know, and we'll get back to this stuff. And this is why I needed to have 3 colors of markers. So, right, so there's this concept of an art gallery problem. Or sometimes it's like Watchman problems or whatever. The idea is that you have some art gallery represented by a simple polygon. So maybe it's like a bunch of different rooms or something, whatever. All right. And what you want to do is put cameras in these rooms so that they can watch all of the different points inside the space, right? So maybe you put a camera here, and then it can watch like this chunk of space, or another camera out here, and it can watch some stuff, and so on. So basically, want to cover a simple polygon with points that can see the whole space. Another way to think about this, right, and sort of the geometry that motivates it, is there's a concept called a star-shaped polygon. So a polygon is star-shaped if there's some point inside the polygon that can see every point inside there. So you can think of star-shaped polygons as something like a generalization of convex polygons, but the idea would be it's still parameterized by like some like angle from a point inside the interior of it, but they can be deformed in some way. So the idea is that here we're going to try to like cut this thing into star-shaped pieces. So we'll throw a vertex here, and then maybe this guy can like see all of this stuff going out here maybe. Right, so like this whole region would be visible from this point, right? And so similarly, then we'd put like another vertex, I don't know, maybe here. This thing can then see these things, like maybe see some more stuff kind of around the corner. Right, you get the idea. So we want to basically put these points inside this space so that we can cover the whole polygon with these different cameras, right? So the challenge is to do it with the smallest number of pieces, usually, right? That's not usually possible, right? So there's finding the smallest number. Smallest number is NP hard, and actually even kind of hard to approximate. But we'll see the best that you can kind of do. So this is sort of the best known approximation for this problem. And it's actually optimal in the worst case, right? So sometimes you actually have to do this. So the first point, right, is that at least n over 3 is necessary in the worst case. And the proof for this is that you basically just draw something that looks like this, right? So you have like a bunch of these little combs going out here, and there's no vertex that can see all of the points inside the comb. So you just push these down here. So you have to put at least one camera at any point on one of these combs in order to cover all of the bits inside each of them, right? So that's the worst case solution. It turns out, though, you can always do at least n over 3 rounded down, right? And here's how you do it, which is you 3-color a triangulation, right? So here's one way to get n over 3 is to 3-color a triangulation. This is always possible, right, because of the dual version, right? So each of these polygons has degree 3. And the dual is going to be this planar map. So we can always find some 3-coloring, right? So here's kind of a picture. Right, so we'll draw these triangles here. So a 3-coloring is basically some assignment of colors from one of 3 different possibilities to the vertices of the polygon. So I'll just go through how this works here. So you can pretty much do this in a greedy way. So we'll color this vertex green, and then the neighbors of this vertex have to be different colors. Right, so we'll color that one green. This one here now has to be black. Similarly, this one now has to be red. And then for trees, it's not, right? Because coloring a tree is pretty easy. So it turns out that this is not so bad because of the specific details here. In fact, what happens is that if you just try doing it like what I'm doing right now, you'll find that once you make some initial assumptions on the color of one of the vertices, you're just completely constrained in the next color that you have to pick. And you can always do it with at least 3 here, right? I mean, in general, though, coloring a graph of any sort is typically an NP hard problem. But because these graphs are pretty easy, this turns out to be something that you can do very quickly, right? So now that we have this thing constructed, here's how you construct an art gallery covering of this polygon, is that you just pick any one of these colors, right? And that color is going to completely cover the polygon. So we basically just find the coloring which has the smallest number of, I think I can make this one black here, right? Yeah. Yeah, because I can't color those both red, right? I have to color one of them black. OK, so here's what you do, right? So any color can see all points in the polygon. So we basically select whichever of these has the smallest number of vertices, and that's going to be 4 over n over 3. So we just select vertex set with smallest size. This covers the polygon in n over 3 vertices. So easy, right? So that's the simple 3-coloring theorem for polygons and the sort of art gallery problem. Yeah, it's a thing you can do, right? It's related to the star-shaped decomposition of polygons. I don't know. I think the real moral of the story here, though, is that if you give your problem a cute name, people will pay more attention to it, right? The idea is that there's some sort of art gallery, and you have these cameras and watchmen and stuff. Yeah. OK. How much time do I have left? Because overtime right now? All right. I think this is probably where we're going to stop. I wanted to say a couple of things about some extensions of this really quickly. The first is that in high dimensions, polygon triangulation, or basically just triangulating some arbitrary shape, is insanely hard, right? So in 3D, it's actually NP hard to detect if a triangulation even exists for some arbitrary object. And if you want to triangulate it anyway, you may sometimes need to add in additional vertices, and you might have to add in up to n squared extra vertices in order to triangulate some general like mesh in 3D. So it's really, really hard in 3 dimensions. And once you get to higher dimensions, it's sometimes not even possible, even if you have an unlimited number of vertices, to construct something which matches a given boundary. This is because in high dimensions, there are so-called non-triangulable manifolds, which don't show up until you get to 4D or higher, right? And so these things, like, you just can't even cut them into triangles in the first place. It's just not even possible. So, even if you used as many vertices or triangles as you wanted, you couldn't do it. So really, the fact that triangulation works out so well is kind of an artifact of 2D geometry. It's not something that necessarily generalizes so well when you get to higher dimensional spaces. And the other thing, too, is also Delaunay versions of this. So a variation on this problem of polygon triangulation would be to find a constrained Delaunay triangulation. So this is where you want to construct a Delaunay triangulation that contains this polygon, as like some special case. There are algorithms for doing that. They become a little more complicated, but you can basically adapt this sort of insertion algorithms that we've seen for doing Delaunay triangulation. Edge flipping, however, doesn't necessarily work for 3D triangulations. You need to be a little more careful about it. So there are a couple of different algorithms for doing that, but one of the more popular ones involves inserting additional vertices into the polygon. So what you do is that you first build a Delaunay triangulation of the points, then you insert each edge and each face and each tetrahedra or whatever, in however many dimensions you're going to do it, into the Delaunay triangulation. And then you add additional vertices wherever one of the edges of the Delaunay triangulation intersects one of the features of your mesh, right? So you basically just keep throwing in these extra vertices and refining it until you're left with a mesh that happens to contain all of the faces of your original boundary object as cells, right, or unions of cells in this Delaunay triangulation, and the resulting thing is now Delaunay, right? So like NetGen and all of like these like meshers that people use for 3D finite element codes are basically implementations of this idea, right? So the trouble with those algorithms is in the worst case they can be quadratic time, but in practice they are usually okay, right? But you can always like construct inputs that will make them explode or like do something kind of bad. So it's not optimal, but that's just what you have to deal with in 3-dimensional geometry. So I think with that, we're kind of done. Next week we're going to do orthogonal range searching, and I guess you can all go now. So.